All right, so today we're going to look at what's called Intro to Free Body Diagrams and Friction. And like I always tell my students, we're going to kind of do this over the course of three sessions or three note packets. And I'd say if you think there's any chance of you taking college physics, these are the three you want to save, because we're just going to kind of start real simple and then kind of progress from there. But so I just made a note at the top: save for college physics 1 of 3. It's a trilogy, like all good movies, right? So we'll just kind of fill this out as we go. You do want to download this note sheet ahead of time so you can kind of just fill it out. It's easier than having to write everything by hand too. So it says Intro to Free Body Diagrams and Friction. Whenever we are posed the problem involving multiple forces acting on an object, physicists and engineers analyze the problem by using what's called a free body diagram. So we'll say free body diagram. And just because that's a lot to write every time, a lot of times you'll see in the book it just shorthands it by saying FBD. So free body diagram. All right, it says once we draw an accurate FBD, we can add the forces and use our kinematics equations to analyze the object's motion. So basically, we're going to talk about this in our next video, but there's going to be kind of 5 steps for success. And the first step always is to draw an accurate free body diagram, which labels all the forces. Because if you don't have the forces labeled right, there's a good chance you're not going to do the problem right. So before we get into the FBD examples, we just want to do a little quick review of what Newton's second law is. So just take a moment, and if you have to hit pause, hit pause. What's Newton's second law? All right, so if we go back, Newton's second law says F net is equal to m times a. And let's switch colors here. And remember that forces are always measured in newtons or uppercase N, mass is in kilograms, and accelerations in meters per second squared. And then kind of a special example of this, we had talked about in a previous video that the weight that you feel on Earth, W equals mg, is kind of a special case of Newton's second law, because weight is a force, W is weight, and that's a force in newtons. And then we have mass in kilograms, and then we have the acceleration due to gravity, which is in meters per second squared. So I just want to do a quick reminder: whenever you see weight, just think that's a force. Mass is not a force. All right, so our first example, it says, example number 1, you have a stationary block on a table. So as I'm making this video here, I just have my coffee cup next to me. So coffee cup, ooh, it's out of coffee though. But when you have just a mass on a table, think about all the forces acting on that mass. And so we have our block here in this case. So let's look at our block, and it's sitting on a table. And we just want to ask ourselves, what forces are acting on that block? And if you think through this, because that object has mass, it's going to have weight. So that means there's going to be a force that's going down. And so we'll say there's your force of weight going down. And then you're going to think to yourself, well, that can't be the only force that's acting on this block, because if it were, that object would have a net force going down. So we know there must be some other force that's going up. And that force is from the table. And that force is called the normal force. And normal force is just a force that's basically a support force. And what's special about the normal force is it's a force that is perpendicular to the surface. So for example, our table, I'm just going to kind of highlight right here. Here's our tabletop that is in blue, and that normal force is making a 90-degree angle with the surface. So if we were to draw an FBD of this, we're just going to draw a little point. And this would be what physics teachers or professors would call a point mass, because it doesn't really matter what the mass is. It could be a coffee cup, it could be a block, it could be a car, whatever it happens to be. We're just going to represent it as a dot. And on that dot, we have a force going down that we're going to call its weight. So there's the force vector going down, W. And then equal in magnitude or strength, but opposite in direction, is the normal force, N. And so if we look here, we started with a picture and we converted it over to an FBD, because an FBD is a really simplistic way that somebody could just see this picture and they'd be like, oh, there's 2 forces acting on a mass. So it said the FBD should include all forces acting on the object. So at this point, you'd have to ask yourself, okay, are those all the forces acting on the object? And we'd say yes. So if we look, when we add these forces, then it says F net is equal to MA. So we're going to say, okay, the normal force is going up and weight's going down. And I'm just going to put a little reminder in here. our normal coordinates would look like that, where we define positive x to the right and positive y would be going up. So according to the way we normally define coordinates, I would say that n is a positive force. The normal force is a positive force. And w, in that case, would be a negative force. And we know that when we have n going up and w going down, it's going to sum to 0. So n minus w equals 0. Well, that actually gives us a nice little equation that n must be equal to w. And so in this case, we know that w from above is equal to mg. So what we kind of just figured out then, a really simple example, is that in order for this to be in what's called static equilibrium, the normal force has to be equal to the object's mass times gravity. So basically it's saying is the reason why, like, say you're sitting in a chair, you're an object sitting in a chair, the reason you feel your weight, or mg, is because you have a normal force pushing up on you. If for some reason the chair collapsed or broke, or maybe somebody was mean and pulled the chair out from you, you would lose your normal force, and then you would feel weightless as you fell to the ground because you wouldn't have a support force there. All right, let's try example number 2. A block of mass m is being pulled to the right by a force F. So go ahead, hit pause, and then try that one out. Try first maybe drawing a picture, and then drawing an FBD. All right, so for this one, I'm going to say that there's my block, and it says a block of mass m is being pulled to the right by a force F. Well, just because something's being pulled to the right doesn't mean we can forget about the other two forces we had from before. So I'm going to say, in this case, we have our weight vector still going down, W, and then we have our normal force still going up, and then we're adding on this other force right here. And it says pulled to the right, so sometimes in a physics book they just do something like F sub pull, being pulled to the right. So that'd be the FBD in that case. And then I'm just going to make a note. The net force in this case is not equal to 0. So the net force is going to be to the right, or you could say in the x direction, or x hat. So in this case, in the y direction, you're going to have your vectors cancel, your forces cancel, but there will be a net force to the right. All right, a couple of notes. Number 1, the force of gravity can be labeled W. So that's the force you feel from gravity or weight. Some physics books might label it as F sub G, the force of gravity. And then I remember my college physics book, they'd always just label the force from gravity, they just called mg. So maybe in some future physics class you have a book that uses a different variable. Don't let it mess you up. Just think when they put W, or they put mg, or they put fg, they're just telling you that's the force from gravity acting down. Likewise, some physics books will use an uppercase N for the normal force, or some will actually use an F sub N, force normal. So whichever physics book you happen to use, don't let it throw you off. Just think, okay, what's the question saying? And a lot of times you can figure out, oh, that's just the force normal. That's normal force. They might use a different variable. All right, let's try page number 2. Free body diagrams continued. So it says, often a rope, a cable, or a wire is attached to an object. The force from a rope, cable, or wire is called tension. So I'm just going to highlight this here. Whenever you have a rope, cable, or a wire attached to an object, they label that as a tension force, uppercase T. And then you might say to yourself, well, kind of what we just talked about in the last page, some books might call a tension force uppercase T, but some books might call it F sub T, like that. So force tension from a rope. The big thing, tension forces can only pull or push on an object. So think about that for a second. If you ever had a rope, or maybe you're taking your dog for a walk, can that leash pull the dog, or does the leash push the dog? So hit pause and then we'll come back. All right, so I was actually taking Lucy the dog for a walk just the other night because it's been super nice outside. And it was made pretty darn clear to me is that ropes can only pull. So Lucy tried to get away and I pulled her back. She tried to go the other way, I pulled her back. Ropes and cables or wires, they can only pull. So tension is a pulling force. So let's say tension forces can only pull. I could never take my dog for a walk by trying to push Lucy along with the leash because that's not the way leashes exert forces. All right, so let's try example number 1. This time looking at tension forces. It says a block of mass M1 is attached to a second block M2 via a pulley. And this is my best attempt to draw a little pulley right here. On a frictionless table, draw the FBD for M1 and M2. Now, the thing about FBDs is that whenever you have a mass, they get their own FBD. So, for example, for mass number 1, try to draw the FBD for mass number 1, and then when you feel good about that one, try to draw the FBD for mass number 2, and then when you're ready, hit play and we'll be back here. All right, so for mass number 1, and I'm actually going to go right onto the picture at first. So there's the mass. We always have weight as a force that always acts down. So there's our force vector of weight going down. And then just like the previous page, we have the normal force going up. And the only thing that's new in this problem is that we have it hooked up via a cable to a second pulley. I'm sorry, to a second mass. So in this case, you're also going to have a tension force going that way. And then so the FBD for this one, on FBDs, you don't have the pictures, you just have the point mass like we talked about. You'll have W going down, you'll have the normal force going up, and you'll have the tension force going to the right. All right, mass number 2, let's switch to green. What force always goes down? It's weight. So weight is a force that always acts downward. Put my green dot over there. And in this case, a lot of times I've had students tell me that the force going up in this case would be the normal force, but mass 2 actually does not have a normal force. And the reason why is because it's being suspended up in the air. So in order to have a normal force, you have to be touching something. And if I were in class, I'd make the joke, looks like mass number 2 got in trouble at school. And then a student would be like, why did mass number 2 get in trouble, Mr. Laurent? And I go, well, it got suspended for something. Sorry. So mass number 2 is suspended. So in that case, it's being suspended by a cable. So in this case, tension force would be going up. So this force is not normal, it's the tension force. All right. Example number 2, in your college dorm, you hang the following sign held by 2 ropes. Draw the FBD. So go ahead and take a moment, try to draw the FBD of your I love physics sign. Much better. All right, so here, I'm just going to draw a little point mass here. There's our physics sign. And then in order so all your college dorm mates can see it, you want to suspend it high in the air. And you notice that this is a cable or rope. And we said that cables and ropes can only pull on things. So we're going to have 2 forces. Let's go like that. So right here you have, there's one tension force. And there's another tension force. And ask yourself, is that all the forces acting on this object? And it's not, because you always have the weight force going down. So there's our FBD for our sign that's being suspended. All right, a couple more. We're going to do a whole bunch of these because if my general philosophy, and Kayla and I talk about this a lot, is you got to be able to draw the picture of your FBDs right, because if you can't draw the picture, then when we put the math in, then it doesn't make sense because you're doing math on something that's not even physically accurate. So it's really important to be able to draw the picture accurately. So example number 1 for our practice, it says a block sliding down a ramp. And then in example number 2, you have a block being pushed up a frictionless ramp. And let's just say, because we haven't talked about frictionless or friction yet, let's just say this is also frictionless. So no friction. All right, so for this one, there's our point mass. And what force always goes down? It's weight. So there's W. And now the tricky part about this one is this is a ramp. So it's at an angle. And normal force is always perpendicular to the surface. So our normal force in this case is kind of crazy. But it's actually making a 90-degree angle with that ramp. So in this case, our FBD looks a little different than we've drawn before. You got W going down. And the normal force is going to be going up and to the right like that. All right, for this one over here, weight is a force that always goes down. Our ramp has got a different angle to it. So in this case, our normal force looks like that. Still, if you trace it down, it's making a 90-degree angle with the surface. And then you have some force of pushing going back this way. So our FBD for this one would be weight going down, normal force up and over, and then some force being pushed up the ramp.